So now that we have understood the virtual memory, we can examine the address translation in RISC-V. To understand address translation in RISC-V, first we need to understand a mechanism for address translation called the radix-based page table. So instead of showing you the RISC-V radix-based page table first, I found this interesting figure in this article that the reference appears in the bottom of the screen that hopefully are going to help us understand how radix-based page tables work. So what we have here is the virtual address that the processor would be accessing. This is for a 64-bit machine. And as you can see, we have divided the virtual address in different segments, and the offset that are the 12 bits that I use to offset into the page are here. Those don't need any translation. And then I have divided this portion of the address into different segments that I call them indexes. And the way I'm going to access the page table is that there will be a control register that contains the base address of the root table. So I access the root table with using as an offset only these bits from the virtual address. That will give me a page table entry. And then I take that page table entry as the base address for the next level in the page table, and I use the index 3 to find what is the page table entry at that level, and I repeat the process now with the index 2 and the address that I just got from that level of the page table. I go to the next level, and finally I get to the bottom level of the page table, and this will be where I'm going to find my physical address. So this is how radix-based page table works. So now if we look into the RISC-V processor, we'll find this register that's called the Supervisor Address Translation Protection Register, SATP. And in this processor, we're going to find a field that is the physical page number. We're going to find another field that is the address space identifier, and then we have the mode. The mode tells the mode is a single bit that tells you how I do the translation. Basically, it's saying if I use a directly mapping to the page table or whether I'm using the radix-based page table. And all these fields are called WARL in RISC-V. That's terminology adopted by RISC-V to indicate that these are fields where you can write any values, but you only can read legal values. So which means that no write will produce an exception when going to these fields, but if I write a value that it's considered illegal for that field, the value that we're going to read is a legal value. We have seen a very important example of WARL from the beginning of the course when we set the register 0. You can write anything to register 0, but when you read from register 0, the only legal value that you can read is the value 0. And those fields in here are the same. And now let's look at the address translation in RISC-V. We have the page offset like we have seen before, that the bits that are not translated. And then for the virtual address space, I have 32 bits, and I have the virtual page number 0 and 1. For the physical address space, here I have a larger address space. I have 34 bits, and I have the physical page number in 0, and the physical page number 1 actually has 12 bits instead of 10. So let's look at my RISC-V page table entry and see all the components that I have in a page table entry in RISC-V. I have a valid bit that indicates whether this entry is valid or not. If this entry is not valid, there is no meaning to any of the other bits in the entry. Then I have a bit that tells me whether the page is readable, one that tells me whether it's writable, and if a page is writable, it must be readable as well. A combination that will say writable and not readable is reserved for future use by RISC-V. And another one that tells me whether the page is executable. If I fetch an instruction from a page that's not executable, it will gonna generate an exception. So all the text of the program has to be placed into executable pages. And if I have a combination of the bits X, W, and R that are all zeros, this indicates that this page table entry is a pointer to the next level in the page table, just like we saw before that we have those pointers, but here we're going to have the pointer with the different values. If these numbers here are not all three zeros, if any one of them is not zero, then it is a leaf page table entry that contains the actual physical address. The U indicates whether it's this page is in the user mode, a user program, as opposite to operating system or kernel level program. A user program can only access pages that are in user mode. So this is the way that I protect the operating system's page from access by the users by ensuring that the bit U is not set. And then I have a global bit. A global bit is a global page is a page that can be accessed by any program in the system, and it can be used for global constants or different information that should be available to all programs in the system. Then I have an accessed bit that tells me whether this page has been accessed, read, written, or executed since the last time that it was brought into the memory. And then I have a dirt bit that indicates whether this page has been written. So of course, for any page table entry that has the dirt bit 1, the accessed bit also has to be 1. But there is a finer control of access here where the access bit can record whether the page has been read. And then I have 3 bits that are reserved for the supervisor software and that are not used in the user mode. So let's talk about page replacement. To reduce the page fault rate, we would prefer to use a least recently used algorithm for the page replacement. However, we have seen that a least recently used algorithm for a full associative memory system is not practical because we cannot keep the exact order in which all the entries in the table, in this case all the pages in memory, have been accessed. So what we're going to do instead, we're going to create an approximation to the least recently used algorithm by having a reference bit that's called a use bit in the page table entry set to 1 when the page is accessed. And periodically this bit will be cleared by the operating system, and therefore a page that has a reference bit equals 0 has not been recently used. The way this is implemented, a simple way to implement this is to divide the page table entries into regions. In this case, we are illustrating a division into 4 regions. And the way we're going to approximate the least recently used algorithm is whenever we access a page, we're going to set the use bit of that page table entry to 1. So in this picture, all the boxes that have this dark gray color are indicating that that page table entry has been accessed since the last time that it was cleared. And then as time goes by, so when I need to do a page replacement, what I'm going to do, I'm going to scan from my search pointer, the point where my search pointer is, I will scan down the table, and the first page table entry that I find that does not have the use bit set, I'm going to replace. So the way it's going to work is that at some point, I'm going to clear all the bits in that first segment of the page, and I'm going to move the search pointer to the beginning of the next segment. So now whenever I need to replace, I'm going to be searching from that segment. Then as time goes by, what will happen is that some of the entries in the segment that I have just cleared will have their use bit set because they have been recently accessed. And then after a certain amount of time, what I'm going to do is I'm going to clear the next region of the page and move the search pointer down. So as you can see, the search pointer is always at the point, at the region of the table that I have cleared the farthest in the past. So the one that has for the longest have not been cleared. So which means that any entry that does not have the use bit set in that region of the table has not been used for a certain amount of time. So this is one algorithm that can be used to approximate the least recently used algorithm in a very large page table that is fully associative. There are alternatives to this algorithm that you're going to discuss and learn in your operating systems class. Let's talk about writes now. If I try to do a write to the disk, it's going to take millions of cycles. And what we're going to do, we're going to block at ons, not on the individual locations for the write. So if we try to do a write through for memory, virtual memory is impractical. So I cannot, for every write that the processor does to the memory, do a write to the disk. So I must use write back. And if I use write back, I must have a dirt bit in the page table entry like RISC-V does. And this dirt bit will be set when there is a store to allocation in the page. So one of the questions when we start looking into the this whole virtual memory, we need to ask is, where are those page tables that we're talking about? Those page tables are in memory. Remember when I did the RAID X3, I had to do several memory accesses actually to find the actual physical address. So we have been spending quite a bit of time on the design of the data path, on the design of the cache system for our memory hierarchy, to try to gain every cycle that we can in the execution to make the execution faster. So now let's contemplate what we may have to do in order to have virtual memory. So we have the processor and with an internal cache. We have the memory, and the page table is in the memory. So the processor will start the execution of an access, whether it is to fetch an instruction or to access data, by issuing a virtual address. In order to find out what is the corresponding physical address, the processor has to access, we have to access the page table. So that implies that the virtual address has to be sent to the page table, and the page table will then determine what is the physical address. Remember all those accesses that I had to do, and so I may have several memory accesses to do in order to find the actual physical page number, and then that physical page number then would go into the cache for an access. And then the data would be provided to the processor. Of course, we cannot have a memory access or several memory accesses having to happen before I can even access the cache, because that would undo all the work that we have done in order to optimize access, to minimize the number of cache misses, and to optimize our data path. So we need a better solution. The better solution is to actually have a cache of the translations, and this cache of the translations is a translation look-aside buffer. As you can predict, there is lots of locality in these translations, because also the processor does one access to a memory page, giving spatial locality. There is a very high likelihood that subsequent accesses will be to the same page, and due to temporal locality, there is a high likelihood that the processor is going to access these pages again. So what we're going to do is to have this TLB, that is the translation look-aside buffer, that's contained inside the processor, and that remembers or stores the most recent translations that have been done. So my translation look-aside buffer will be accessed by the virtual address. So I'm gonna send the virtual address to the translation look-aside buffer. If I am in luck, the translation look-aside buffer will contain the physical address, and the data will be in the cache, and I can send the data to the cache. It may occur that when I send the virtual address to the translation look-aside buffer, that the TLB does not have the translation, because the translation has been replaced, so it has been a long time since I accessed this address. In this case, what I have is a TLB miss. I go to the page table to find out that what the translation is. I bring that translation back to the TLB, and then I can complete the access. However, in some cases, I may go into the page table and I find that the page is actually not in memory. In this case, I can have a page fault that will go into the disk, and then the disk will bring the replacement page into the memory, and then I will be able to complete the access. The page fault is handled by the operating system. And if I am replacing a dirt page, I must first write the page to the disk before I can do the replacement. And there is an interesting exercise that you may try to do yourself. That's to imagine what's the worst that could happen by executing a single instruction in a RISC-V processor. You have to consider that first you have to fetch the instruction, and you could have not only a TLB miss, but a page table miss when you try to fetch the instruction. And then if that instruction was a load, then and the other thing that could happen is that the page table entries itself, they are in page tables, so that page could also be missing from the memory. So you could have actually two page faults just to access the instruction, and you could have two more just to access the data if you are doing a load or a restore instruction. So you can think carefully about what's the worst that can happen when you are accessing as a single or executing a single instruction in RISC-V. And remember, for each one of these page faults, you have an exception that has to be handled by the operating system. So here is a picture illustrating the translation using a translation look-aside buffer. So I get the virtual page number, and I access my TLB with the virtual page number, and that TLB will give me the physical address. The physical address allows me to go to the physical memory. In some cases, when there is a miss in the TLB, I then go into the page table, I find the translation in the page table, and I access the memory, and I copy that translation in the TLB. And in some cases, the page is not in the physical memory. In that case, I have to first retrieve the page from the disk, put it into the physical memory, and then update the translation, and then provide the data to the processor. Let's talk about TLB misses. If the page is in the memory, then I'm going to load the page table entry from the memory and retry. This can be handled in hardware, but sometimes it can get complex for more complicated page table structures, and in this case, you may have the operating system handling it. So it could be handled in software too. I can raise special exceptions, and I could have an optimized handler that handle this case. If the page is not in memory, then I have a page fault. This cannot be handled in hardware because it takes too long. The processor cannot simply sit and wait for that. The processor has to go and do something else, that is to execute a different piece of code. So the operating system will handle the fetching of the page, will update the page table, and will then restart the faulty instruction and continue the execution of that program. So the TLB miss handler will indicate whether the page is present but the PTE is not in the TLB, or if the page is not present. I must recognize TLB misses before the destination register is overwritten, and I must raise an exception in the case of TLB miss to handle the TLB in certain systems. And the exception handler will copy the page table entry from the memory to the TLB and then will restart the instruction. If the page is not present, then I'm going to have the handling of a page fault. So the page fault handler will use the faulting virtual address to find the page table entry. You locate the page on disk, so the page table entry will have information about how to locate it in disk. We'll choose a page to be replaced. We already saw that approximation to the least recently used algorithm. If the page that is being replaced is dirt, first it has to be written back to the disk. You're going to read a page into the memory and update the page table. And then we'll make the process runnable again, restarting from the faulting instruction. I'm going to stop here and have another part of this lecture to talk about the interaction between the cache and the paging system.